Ladies and gentlemen, I am Professor Syed Murshid, and today I want to share with you a multi-terabit per second hybrid optical communications architecture that utilizes novel multiplexing and modulation schemes. This work was performed at the Optronics Laboratory of the Department of Electrical and Computer Engineering at the Florida Institute of Technology, and my collaborators on this endeavor include my graduate and undergraduate students who are also co-authors on this paper. So, why should we push for and look for higher data rates at multi-terabits per second? Very simple. Data traffic is increasing at 2 dB per year. What it means that the data traffic will increase by 10,000 times over the next 20 years. Obviously, this is a very scary problem to have. There's absolutely no way for us to lay down this kind of fiber, over the next 20 years to support 10,000 times more bandwidth. So we have to explore new multiplexing techniques. We have to find ways to explore new degrees of photon freedom inside the fiber, and we have to also determine ways to find some method of having a spatial reuse of optical frequencies. Furthermore, we also need to explore improved modulation schemes. So with that in mind, we explored and looked into SDM and OAM, space division multiplexing, and orbital angular momentum of photon-based multiplexing. SDM is also sometimes called spatial domain multiplexing or space division multiplexing. So that is what I will primarily talk today. I will also show that SDM and OAM can be combined with WDM. Then I will show a proof of principle for SDM systems and show that the SDM systems do carry OAM. Then what we will show that SDM and OAM and WDM or the entire SDM system can be combined with a simplified PAM4 system. What is a simplified PAM4 system? Instead of using dedicated DSP chips to generate the PAM4 signal levels, we found a way to use incoherent addition of laser beams to develop the PAM4 signal. And then we will show or present a vision for a hybrid architecture that combines SDM, OAM, WDM, and PAM4 systems to push multiple terabits of data per second over a single core optical fiber. And if we look at it, why SDM? Because there have been many review papers that say that the future of optical communication will be based on SDM. The next decade will be based on SDM if we want to push optical communication. And our group at Florida Tech Optronics Laboratory invented the SDM technique in around 2007. That is where we got the patent, and we started publishing it openly around 2008 timeframe, although there were some 2004 publications as well. So to continue further, folks, let's go and look into SDM, OAM, and WDM. So SDM compared to a standard optical fiber system is a MIMO system. A standard optical communication system has a single source, a single detector, and a carrier fiber. There's a one-to-one correspondence between the optical source and the optical detector. Light is launched from the source into the optical fiber, follows a meridional ray or a meridional path inside the carrier, and appears at the detector. Now, and on the SDM side, it is pretty similar. If we only had one source and one detector, it is pretty similar to standard communication. However, SDM uses, instead of one source, multiple channels of light, multiple sources of light. Each of those are launched at a specific angle. They all come inside the fiber with the help, or they are combined inside the fiber, or they are launched inside the fiber with the help of a multiplexer or a beam combiner module. Once light is launched inside the carrier fiber, it follows helical path inside the fiber and it appears at the end of fiber as concentric circles. These are basically different rings of different radii. So spatial filtering techniques can be used to demultiplex them. So they go into a demultiplexer or a beam separator module or a demux that simply uses a spatial filtering techniques to demultiplex them and routes them to channel 1 and detector 1 and channel 2 and detector 2 and channel n and detector n. The basic difference between these two, the optical energy inside the fiber follows a helical path. That's the primary difference. Otherwise, there is a one-to-one correspondence between channel 1 source and channel 1 detector, channel 2 source and channel 2 detector, and channel n source and channel n detector. Plain and simple. So if you wanted to go and look at the mathematical model, you could start with a TEM00 mode or go to an LG00 mode where L equals P equals 0. If L equals 0, there's no OAM. But if you take an LG mode of the order 0L, then there will be only one ring, 0L, only one ring. But if L increases to be greater than 0, then they will have an azimuthal component associated with that. And due to the azimuthal index, it will have some OAM. And also, as L increases, I will have larger radii. So if I have multiple channels with 0L, where L is different, but the order is 0, I can have multiple rings. And these rings could be independent of each other. So that's the basic math behind it. Very simple, basic, fundamental math if you wanted to look at it. So now if you go and look at it, I could call it SDM00 or LG0L or SDMXL because LG, this order is always 0. But in SDM model, what we say that although this stays 0, but the first ring or the 0th order SDM ring is 0, the first order SDM ring is 1, and then 2 and 3 and 4. So SDM 0th ring, first ring, second ring, third ring. So there are 4 rings, 0, 1, 2, 3. Okay, or 1, 2, 3, 4, whichever way you look at it. So what we do over here, these rings are basically again LG0L, but they are picked in a fashion that the energy intensities do not interfere. And if the energies do not interfere, I can have 4 different channels as shown over here to go through the optical fiber. The same core, 4 channels, those are independent of each other and they do not interfere with each other. Okay, folks. So with that in mind, if I take 2 SDM channels and launch into one carrier fiber, 2 sources into a carrier fiber, we taper the input fibers to allow better coupling efficiency because the real estate over here is limited. So launch those at the specific angles, okay, and you have 2 rings over here represented by this. And if you had a third fiber, you can have a third ring. And if you had a 4th input fiber, you can have a 4th ring. Okay, so they come out, you launch them at a specific angles, and they come out at the detector as circular rings. That is simple SDM system. Okay, so that is what is shown over here, 2 channels at different angles, and combined when both of them are on, we get this thingy, only one of them on either this or that. You could also simulate it using the Opti system and Opti BPM, and the results are pretty similar. You could also develop it using another technique that taper the carrier fiber and have the input fiber over here normally, or any different way you want it. These are the different angles that we launch them in over here. And what we have at this point, all the 4 channels are off, all the 4 channels are on, and all the different combinations. So there is a one-to-one correspondence between the input and output. And you see these channels do not interfere with each other. Okay, so that is the gist of an STM system. Once I have that, Okay, I can combine them and we have tested it up to a kilometer. The attenuation actually is about 5 to 10% higher for the outermost ring because of the helical propagation. The outer channels travel slightly longer length, effectively longer length. So slightly higher attenuation, but the dispersion actually is lower than the standard multimode optical fiber. And again, as we mentioned, there is an azimuthal component L over here. This tells that there will be an OAM. So we go and look for an OAM. What we do, as Shevchenko et al. Basically told us to a very simple method that if you launch at a specific angles, and if the fiber has, or if the channel has OAM, all you need to do is put a tiny little wire in front of that channel. And if there is an OAM, let us say it is going clockwise, then instead of having the shadow a straight line, because of the OAM of the photon, the shadow will be going this way. And on this side, instead of the shadow being here, it moves over here. So this is the clockwise OAM. And exactly the opposite on a counterclockwise OAM. So this is the simulated result. This is the actual real world data that supported it. So what we can say that yes, indeed, there is OAM in there. And we saw over here, this is actual data. We just took multiple pictures at different angles and see that actually the OAM is rotating. If I go complementary angle 7 and 7 prime, these complementary angles, then L will have plus and minus values exactly the same magnitude or same value, but opposite spins. That is what it is showing. So here I have a clockwise OAM, a counterclockwise OAM, clockwise OAM, counterclockwise OAM. Simulated result using uh, a simulation tool, and here is my experimental result. Now, if I have these two over here, and this was done using Zmax, okay, now if I have these two channels, they are complementary, let us say both of them have exactly the 7 degrees, then they will be basically the same rings, but one ring would be moving in a should have a clockwise OAM, and the other will have a counterclockwise. If we do that, then both of them would fit over each other. So on this same location, I can have two channels with opposite OAM, or I can have an OAM based multiplexing. That is basically what we are showing over here. And then I can show that instead of two channels, I can have 5 SDM channels in a fiber with a clockwise spin, and I can also have 5 SDM channels with a counterclockwise spin. So what it allows us to have 5 SDM channels on a single fiber, but 5 of them do have clockwise and 5 of them do have counterclockwise spins. So effectively, I have increased the data capacity by an order of magnitude. Okay, so I can combine SDM and OM. Now, WDM carries the water in all optical fiber communication system as we speak. So does SDM and OM support WDM? So in order to look for it, what we said, okay, let's take a green laser source and another red laser source on complementary angles. Only one of them, they show the rings and their OAM causes a shadow. But when I turn both of them on, then they should be at exactly the same location. Instead of getting a green and red ring, I should be getting only a yellow ring. And wherever the red is blocked, I will see the green, and wherever the green is blocked, I should see the red. So that is basically what we did over here, folks. See, and here is the real world data. This is my red channel. This is moving in a counterclockwise direction. So you see, instead of the shadow being here, shadow moved out in a counterclockwise direction. And this is my green channel moving in a clockwise direction. The shadow is distorted this way. And when I turn both of them on, they are not up to scale over here, but when I turn both of them on, then what happens? The green and red come exactly at the same location because they are at complementary angles. They are occupying the same location, despite this one roughly, let us say 632 nanometers, and this one 532 nanometers, 100 nanometer separation, but they still occupy the same physical location inside the fiber. So the location of the STM ring is independent of the wavelength. And this is what, if you go and look at the MATLAB intensity plot over there, you see that the profile says that they are exactly at the same location. So what it tells us that I can now combine SDM, OAM, and WDM. That is pretty much what we are proposing over here. I can combine all the three together. Okay, so here are different SDM channels at different wavelengths. Okay, different WDM channels at different wavelength. I can combine both SDM and WDM. So now SDM, WDM, and OAM there, and put an OAM, they are carrying their opposite spins with plus minus L, plus minus 7 degrees and plus minus 15 degrees. So they have opposite L's as well. So I have SDM, OAM, and WDM combined together. Okay, so now let us go and look at the proof of principle of SDM. Once we have established that SDM, OAM, and WDM can co-propagate and they complement each other. Okay, so what we do, we simply take two tunable XFPs, okay, both of them operating at about 10 gig, 9.90 to 11 point something, so between 9 to 11 gig, okay, and we tune them to exactly the same wavelength. We launch them inside a fiber, and there are many different ways to mux them and demux them. So we launch them inside the fiber, mux them together. They go inside the fiber following helical path, and they come out as two rings. Okay, so here the two rings come out. Okay, at this location, I focus it down. Here are the two rings. Now what we do, we put a mirror here, but the center of the mirror has a hole. So the smaller center ring, this simply passes through the hole into this detector, and it is focused into a fiber and a DCA, digital communication analyzer. The bigger outer ring that hits this surface of the mirror, it is reflected over here and focused by this particular lens and into this particular fiber. So this is the DCA on the other end. Okay, once I combine those two together, I separate them. This is my spatial separation. Okay, and this is how the experimental layout looks like. Okay, and this is my eye diagram. Reasonably good eye diagram with 68 and 53 picoseconds for the inner and outer eyes, and my BER somewhere between 10 to the power minus 9 to 10 to the power minus 5. So reasonably good BER, reasonably good extinction ratio and jitter and all those things. So effectively, I can recreate my bit pattern for both the center and outer channels. And these are all the different performance parameters that we have. The beauty is that all the over entire C band, both channels, both the inner and outer channel at exactly the same wavelength. These are my center channel or the inner channel, and this is my outer channel. Exactly the same way. And we have all the different parameters, and they look reasonably good. So in conclusion, we have demonstrated that an SDM communication system that allows the spatial reuse of optical frequencies, okay, and we have also shown that SDM and OAM-based multiplexing is possible in optical fibers. And we have also shown that SDM and OAM both complement WDM. And we have also shown SDM channels with two channels both operating at 10 Gbps, 10 gigabits per second using TXFP, operating at same wavelength with good eye opening and BER. And we can use it for LAN applications. So how do I complement it for a PAM4 application? So a typical PAM4, let us say that I have MSB and LSB. They combine when both of them are 0, I have 0, 0. Well, LSB is 1 and the MSB is 0, 0, 1, 1, 0, and 1, 1. These are the standard things. Now I said instead of using the dedicated PAM4 chip, what if we take three laser sources, two of them driven by the MSB and one of them driven by the LSB? When all three are off, my output is 0, the level is 0. Only LSB is on, level is 1. MSB, laser 2 and laser 3, they are running in parallel, shorted together. So when the MSB turns on, both laser 3 and laser 2 turn on, and I have a level 2. And when all three are turned on, we have a laser 3. The beauty is that they do not interfere with each other. And as we already demonstrated in SDM, that multiple channels of light of exactly the same wavelength propagate through the fiber without interfering with each other. And we basically proved the same thing again. So if I could do that, then what I can do, I have this, all the other three PAM4 signals coming at an SDM channel here and at another one at a different angle. And then I can have OAM associated with these because of the different angles. And also I can have in each of them, I can have the entire C band running into it. That is the whole game plan, folks. So if we go and do that, here is the simulated version using Zmax that tells us that yes, I can have SDM. I can combine 3 laser sources here and 3 laser sources in each channel, and I will get my SDM channel, very similar to what we used to do. So once we do that, laser source 1, 2, and 3 running in parallel, one is separate, and you combine them together, and here is my PAM4 output. So now we go and apply it to some real world applications. Okay, 1310 nanometers to both of the other sources operating at 10 Gbps. Okay, 200 by 230 micrometer, not millimeter, please excuse us. It is 200 by 230 micrometer multimode fiber, 2 meter long. Okay, at 1310 nanometers, 10 plus 10 give you 20 Gbps because 10 gigabaud, 20 gigabits per second. The same thing now at a 62.5, 125 micron fiber, 35-meter long at 850 nanometer, 10 Gbps plus 10 Gbps, 20 Gbps. Or I can take 225 Gbps QSFPs, combine them together at 1310 nanometer in a 125 micrometer fiber, and it is data after 1 kilometer length. So I can even operate it at 1 kilometer, and the extinction ratio and OMA and RLM, they are all reasonably okay. So this is the data after 20 for 20 Gbps, okay, and this is the data at 50 Gbps data rate after a kilometer at 1310 nanometers. So effectively what we have shown, folks, see that SDM and OAM and PAM4, they can all combine, work together. So now I'm going to present a vision for a hybrid SDM architecture that combines SDM, OAM, WDM, and PAM4. So if you have 140 Gbps baseband, take 5 SDM channels, go to the photonic layer, you get 5 terabit per second. And on top of that 5 terabit per second, take OAM, you get 10 terabits per second. And then on top of OAM, if I add PAM4, I get 20 terabits per second. On the contrary, instead of that 40 GB, if I take 50 gigabit per second channel, add 5 SDM channels, 250 gigabit, add 2 OAM channels, 500 gigabit, 1 terabit per second I will get after the PAM4, 2 bits per symbol. And then if I have 200 WDM channels, then I'm looking at a 200 terabit per second optical communication architecture. So ladies and gentlemen, in summary, we have presented a combination of SDM, OAM, and WDM that leads to an order of magnitude increase in data capacity. It adds 2 new degrees of photon freedom to optical fibers, space, and OAM. It combines SDM, OAM, and WDM with PAM4 modulation scheme, and it is applicable to existing and future LAN networks for LAN applications for beyond 400 Gbps PAM4 signals, and it also supports bit parallel architecture as well as physical layer data security. We are also looking into that. So there are many different possibilities. Okay, so at this point, I'll stop over here, folks. I'll thank you very much for your attention, and I'll be happy to take any questions or note any of your comments. Thank you very much.